All right, everyone, welcome. As promised, we're going to continue on from the demo earlier today and talk about the Gradle Worker API a little bit. First of all, let me introduce myself a little bit. My name is Gary Hale. I'm a principal engineer at Gradle. I hail from Jacksonville, Florida, so I'm a good long ways from home. As an engineer at Gradle, I spend the vast majority of my time working on the Gradle open source product or project. But I also spend a good bit of time teaching Gradle. So if maybe any of you have attended any of the online virtual trainings that we do, I teach a number of those. And when I'm not writing software, I'm a big fan of craft beer. So if you're looking to bribe me and maybe get your favorite wish list item into Gradle, a good hoppy IPA would be a good way to start. I'm going to turn over to Paul here and let him introduce himself. Go ahead, Paul.
Hello, everybody. Spend most of my time working on it. And before that, I've been like writer of software science. I won't say the number, but too many years. And yeah, in my spare time, I'm a dry stone builder. I like that. It takes me quite a bit of time. And mostly at that place, which is far away from here. So yeah, the flight was long. And like Gary's lover of beer, I'm a lover of wine, so we have plenty to share.
All right, thanks. Okay, so one thing that I'll ask of you is that if you have questions during the talk, please go ahead and raise your hand. Let me know. We'll certainly try to answer them. The more interactive this is, the more interesting it's probably going to be to you. The more interesting it'll be for us. So please feel free to ask questions at any time. Okay, so what are we going to talk about today? First of all, I want to talk about why we created the Gradle Worker API. What were some of the motivations? What were some of the problems that we were trying to solve? Then I want to talk about kind of what problems it does solve. What does it do? And then finally, we'll talk about how it works. And Paul's going to do some demonstrations of a use case project, kind of show you, what it looks like without the Worker API, and then some conversions to different usages of the Worker API. Okay, so why did we start looking at the Worker API? Well, last year we recognized that Gradle performance was a little bit of an issue, and that there were some things that we could do to potentially help that. Part of this was driven by some of the needs of the Android community. And so with the Android plugin that Google had written, smaller projects, were just fine, but once you got into very large projects, you started to have some significant performance problems. And it would have been very easy for us at Gradle to stand back and say, well, Google owns the Android plugin, it's their problem. But the reality is that the reason why some of these problems were there was because they were pushing the boundaries of the capabilities of Gradle. And they were doing certain things because Gradle didn't provide the capabilities that they needed. And so we started looking at some of the things that we might do to help kind of clear the path to improve the Android plugin. And what we also realized is that a lot of the things that the Android plugin needed are things that would benefit any build, and not just Android builds. And looking into this, we recognized that there were some new APIs that were needed. And so the Worker API is one of those APIs that we identified. So what can we do with the Worker API? Well, as we discussed a little bit this morning in the keynote, we can run in-process workers. And this allows us to basically take our tasks, break them up, run work in process in multiple threads. We can also run out-of-process work. So this is what we were referring to as worker daemons earlier. We can take work, break it up, and then run it out of process in a completely separated or completely isolated environment. And what we introduced with this is this concept of isolation modes. I'm going to come back and talk about isolation modes in a little bit. So how do you speed up builds? Really, how do you speed up anything? How do you speed up digging ditches? Well, as it turns out, there's really only two ways to do so. And anything that you do is going to fit into this. Number one is do less work. I could dig a smaller ditch. The other way is do more work in parallel. I can get more people helping me dig that ditch. And so with the Worker API, what we focused on was the ability to tackle these two concepts, right? Being able to do less work and to be able to do more work in parallel. So when we talk about doing less work, what are some of the ways that we can do less work? Well, one thing is when we build class loaders are very expensive to build. Loading classes are very expensive. And so if we're constantly rebuilding class loaders, we're doing a lot of work that maybe we don't need to do. We also have the concept of Java exec, right? Being able to spawn processes, that's a very expensive operation. It doesn't matter what platform you're on. Spawning a new process, initializing a JVM, rebuilding class loaders, reloading classes, that's a lot of work, a lot of overhead, especially if the amount of work or the unit of work is really, really small. And so fundamentally, what we want to be able to do is do more caching, right? Caching certainly at a class loader level, can I reuse loaded caches, but also at a process level. Having like a long-lived process is a form of caching. And that's what worker daemons are intended to do. This isn't the only thing that they do, but they help your build do less work. So let's take a look at what this means. Let's imagine that I have a build where I have a number of tasks in this build, these foo tasks. And these foo tasks, whenever they run Java exec to spawn an external process. And so what happens is we spawn a whole new VM, we spawn a whole new process, we initialize a VM, we load a bunch of classes, and then we do the work that's associated with it. And the next foo task that runs does the same thing. And this could be dozens of foo processes, but every one of them is going to spawn a new process, a new virtual machine, and redo all of this work again. On the other hand, if we do this with a worker daemon, this looks a little bit different. Certainly in the first invocation, we're going to spawn a process, spawn a new VM, do this initialization, and execute our work. But having this thing persistent, having it long-lived, allows us to then just execute work over and over and over again in that process. So we eliminate this overhead of constantly spawning processes. So let me show you another example of how we could use worker daemons. And so in this particular case, I'm not running things out of process. I'm not using Java exec. I'm running things in process, but I have a very heavyweight task that I'm running. And foo1 is a very heavyweight task. When I run it, I do this bit of work and I allocate large chunks of memory. And accordingly, I've taken my VM and I've given it a very large heap size so that it can accommodate these foo tasks that allocate lots of memory. Well, after the foo task runs, then bar 1, bar 2, potentially a bevy of other tasks would execute. But somewhere along the way, we're going to run into the maximum heap size, and garbage collection is going to kick in. And so what happens when we have garbage collection? Well, it's a stop the world event. All of these threads in this process are going to stop until garbage collection is complete. And if the size of this VM is particularly large, garbage collection could be a long time. It could be a couple of seconds. And then the next time another foo task runs, we allocate a lot of memory. We hit garbage collection again. And we get these pauses in our build where nothing is actually happening because we're cleaning up these large chunks of memory that we have. On the other hand, if I use a worker VM, or a daemon, worker daemon, I'm going to spawn a new VM, I do the work out there, I allocate memory. I have the same problem in the sense that the garbage collection is kicking in, but this is isolated to this worker VM process. Meanwhile, in my Gradle build, I can have a much smaller heap size, and while this garbage collection is going on in the worker VM, I can still be running other tasks, which maybe are much more lightweight, much easier to run. Now, as we know, garbage collection is not free, right? There's going to be system, resources that get consumed. But the point is I at least have the opportunity to run additional tasks because I'm not tying the heap size to the build VM. I'm tying it just to the worker VM, which is isolated to the work for the foo tasks. Okay, so let's talk about running more work in parallel. So what we ultimately want to do is fill the empty space. And I'm going to talk about what I mean by filling the empty space here in a minute. But what I'm really referring to is maximizing resource usage here. And by maximizing resource usage, what we're going to do is kind of adopt a divide and conquer strategy. We want to divide the work of our task up into discrete, immutable chunks of work that we can then run in parallel, depending on the resources that we have. And if we're running things in parallel, as you probably know, if you've done any sort of parallelism in the past, one of the things that's really important is this immutability, right? We don't want those units of work to be able to affect each other and produce indeterminate results. And so immutability is very important to running or doing more work in parallel. And when we talk about worker threads, this is what this really helps us to do, is to do more work in parallel. Now, worker daemons can do that for us too, but it's kind of a different consideration. There are more considerations with worker daemons where we're trying to create more isolation than in a worker thread. But worker threads in general are going to help you do more work in parallel. And so what does this look like? Let's imagine that I have a build where I've got multiple tasks in different projects. I'm running it with -- parallel. And kick off the build, and at least initially, I've got good parallelization. So these first, 5, 6 tasks are all kind of very tightly bunched together. But then all of a sudden, I run into a task that runs quite a long time, task 7. And so task 7 is kind of blocking because task 8, 9, and 10 are dependent upon it, and they can't start working until task 7 is complete. And so I have this bottleneck, and you see all of this empty space in the resource usage here where I could potentially be doing work, but because I've got this single-threaded task in there that everything is dependent upon, I'm not doing as much work as I could potentially be doing. If we were to implement the Worker API with task 7, what I would see is something more like this, where task 7 has been broken up into these pieces of work, and then I can do more of this work in parallel. And so task 7 completes sooner, which means task 8, 9, and 10 can start sooner, and the whole build completes faster. And so we talk about running things in process and out of process. And really the proper way to think about this is in isolation modes. What level of isolation do I need? So there's a couple different ways that I can specify that. One is that I have an isolation mode of none. And an isolation mode of none means that I don't want to really have any isolation except for the fact that I'm creating an immutable piece of work. So I'm going to start this piece of work in another thread, and I'm going to reuse the class loader from my task in that thread. Now, if you think about it, there are ways to violate that immutability. I could do some very nasty and clever things where perhaps I set a static property of a class and set it to the project object, and then, in these units of work, I could do things to that project object. Because I'm using the shared class loader, there are some things that I could potentially do there. I would encourage you not to do that. On the other hand, I could create class loader isolation. And I would do this because I might want to use different libraries than maybe are available in my task class loader. So maybe Gradle uses a particular version of a library, but in my unit of work, I want to use something slightly different. Maybe the same library, but a different version. And these will still run in process, but we're going to provide class loader isolation when we run that work. And then lastly, process isolation. I would do this if I wanted to have, say, a completely separate environment. So different environment variables, different system properties, potentially a completely different Java executable that I would use. And so this is our worker daemons here, is what we're talking about. So this immutability that we keep talking about, what this really does for us is it enables us to do parallelism by default. And so what do I mean by this? This parallelism by default. Let's take a look at a non-parallel build. So maybe this is a build that either is not using -- parallel, or it's a build that's only a single project, and so -- parallel doesn't have an effect, because all of the tasks are in the same project. And we run task 1, task 2, and then task 3 is kind of long running, and task 4 and 5. Well, if I use the worker API with task 3, well, I could speed this up a little bit, right? So this is just like what we were talking about with the parallelism, is that, task 3, I break it up into units of work. And then because I know that these units of work are immutable, I can go ahead and start task 4 here. Say task 4 doesn't actually have a dependency on task 3. He just happens to run after task 3 because we are single-threaded without the parallelism. But even though I'm not running with -- parallel here, and maybe task 4 is in the same project, I'm still getting parallelization because the worker API allows me to break my work up into these immutable bits. Now imagine this across all of the tasks in this build, even if those tasks only have a single unit of work that they submit. I start to break this up, and maybe task 2 doesn't have a dependency on task 1, and so I can go ahead and get him started as soon as task 1 has submitted his single unit of work. And then task 3 is dependent upon task 2, so we have a little bit of empty space there. But then task 4 obviously can slip in. Task 5 can slip in a little bit earlier than it would before. And we're reducing that empty space. We're trying to fill that empty space. Okay, at this point, let's take a look at how to use the worker API. And I'm going to turn things over to Paul and let him talk about it.
Sure. So we're going to look at a pretty simple case study, which is generating Java code from WSDL files. As a first step, we implemented a plugin using the good old Java exec that just forks and use a WS import tool. And then we will look at how to leverage the worker daemons, that is the process isolation mode, and then use worker threads. Okay, so let's look. So this is a task, right? So there is some boilerplate for configuration and so on, but the meat piece is here. It's the actual task action. Yeah, sure. So the task action is like processing a set of WSDLs, right? And so for each WSDL, we fork the WS import tool. So it means that if we have like 20 WSDL, we will fork 20 times. And we'll pay the cost for each process we fork. So that's small, but yeah. Okay, that's better. So thanks to the new console here, we can see that it's running serially, and tasks are quite slow. So it takes 14 seconds in total. Okay. So let's now look at how we can change that task implementation. So that's basically how you use the worker API. So in your task, you get the worker executor services injected, and then you simply use it to submit work items. Okay? And so in details, we submit the WS import runnable. I will show you this class in a second. But it's basically the implementation of the unit of work. And then we configure how we'll run this unit of work. And so first, the isolation mode. Here we say process, right? And eventual fork options, system properties, and so on. And we need to set the class path for the forked process, right? And parameters. These parameters actually apply to the WS import runnable. And here it is. So it's simply a runnable. And so the parameters we did set on the configuration previously gets injected into its constructor, right? So that's a mechanism that guarantees immutability, because we have some infrastructure to guarantee that immutability between your task definition and the place where this runnable is executed, being in process or in another thread. And in the run method, we can just implement. So let's look at the code for this. Okay, so this is the same WSDL to Java task. And we still have the loop to process our set of WSDL, but this time we use the worker executor we get injected by Gradle. And we submit this WS import runnable, and we get the configuration. So here the display name is just for nice logging, and we set the params. So here actually, yeah, it's an implementation details, but WS import needs some set of arguments. And we need some fork option because just to set up the XML subsystem in the forked processes. And of course, the process isolation mode. And the class path comes from a Jax WS tools. It's a regular Gradle configuration that provides me with the resolved dependency, basically. And so if we now look at how this runs, so same thing. The sample has like 4 projects generating WSDL. And we can see clearly that it's running stuff in parallel now. And it took like way less time. We did cut about it in half. Okay, so that's nice. But now we will look at, yeah, question? Right, because the parameters so the question was, let's look at the code here. Yeah, so we actually call get files on the configuration that will resolve the configuration and resolve the dependencies. So we get actually files objects. So to guarantee immutability, we serialize and deserialize the parameters. And so file configuration itself is not serializable, so we have to use files. Okay. So now moving on to using worker thread like worker in process. So it's about the same, and we just set the isolation mode to class loader. It was process before. And the other configuration doesn't change. So if we now look at the code, it's quite the same. The main change is to use the class loader isolation. And in that case, we need it because we want the dependencies from Jax WS tools to be isolated in our class loader. And the fork option disappeared because we don't need them. The XML subsystem is already set up in Gradle correctly. Okay. And now if you look at how it runs, it's once again running in parallel, nothing changed here. But it's way faster because like isolated class loader in threads are less expensive than forking a process. In this case, because it depends on your workload. It depends on the task you run. Like in this case, forking dominates a bit the total execution time. Okay, Gary?
Yeah. Okay, so we're still early days for the Worker API. It's still a work in progress. So the Worker API is in Gradle 4.0, where what we have are in-process and out-of-process workers. One of the things that's not quite there yet, in 4.0 at least, is that worker daemons are only build session scoped. So we, at the end of your build or the end of your build session, if you're running a continuous build, the worker daemons will get shut down. And right now we only have support for runnable. But there's more work coming on the worker API. So if we talk about 4.1 and beyond, worker daemons are reused across builds. So certainly 4.1 M1, this is already there. This exists already. So if you were to use the milestone 1 of 4.1, you would have worker daemons that would live with the daemon. So they would live across builds. Every build that you ran, you could potentially reuse a worker from the previous build. Ultimately, what we want to do is give you some level of control over the reuse level. So you might have certain things that you want to run in a worker daemon that perhaps you want to use only once. Perhaps you want to reuse your worker daemon only within the build, but then shut it down at the end of the build. Or perhaps you want to let the daemon run potentially for the lifetime of or let the worker daemon run for the lifetime of the build daemon and reuse it across builds. Some other work that we plan to do here is converting Gradle tasks over to use the worker API. So once we do that, a lot of this parallel by default you'll start to see the effect of that just by using Gradle plugins and things like that. Another thing that we've identified that might be useful is a convenience task for working with the worker API. So some of that boilerplate stuff that we saw in the implementation that we had, like having to inject the worker executor and doing submissions, we might potentially pull this up into some convenience tasks that make that a little bit less work anytime you want to use the worker API. Another very important thing that we want to add is service injection. And so you can imagine a service that we might want to inject into each unit of work would be the worker executor itself. And that allows you to take a unit of work that then in turn discovers new work to execute and submits new work to the worker executor. Right now we only have the support for runnable. Eventually we want to have some level of support for callable. And then another thing that is interesting here too is the composition and chaining of work. So we are aware of certain use cases. We've solved certain use cases with the worker API. We also see additional use cases that we'd like to solve. So you could imagine, for example, a task that produces or submits a collection of work. And then once that work is complete, he wants to also submit work to clean up. And so right now that's a little bit difficult in the sense that you can't get that parallelism by default. By submitting work and then waiting for it and then submitting your cleanup work. And what we want to do is provide some way to allow for this sort of composition of chains of work. And then another thing that we want to add here too is that in-process workers use cache class loaders, make those in-process workers even faster than what they are now. Okay, so at this point, questions? Sure.
So in 4.0, the parallelizable task went away, that annotation.
Mm-hmm.
I assume the intent is to use the worker API instead?
Yes, the worker API is going to be a replacement for the parallelizable task.
Okay, could you possibly explain exactly how when we go from something that you parallelize, a task,
Right.
not the exact company,
Sure.
to use this new mechanism?
Yeah, so the question is, how would something go from a parallelizable task, which was an undocumented feature of Gradle previously, to using the worker API to solve the same problem? And and ultimately what you're trying to achieve is intra-project parallelization, right? So with the worker API, if you think about the parallelizable task, what you had was a task that had a task action, or potentially multiple task actions, and those would simply be run in parallel with other tasks. Well, with the worker API, you could take that single task action, and even if it wasn't possible to split that up into additional units of work, you could have a single unit of work, right? And once you submit that single unit of work and start waiting on it, now I can start to parallelize again. And so that's how you'd kind of do the same thing with parallelizable task with the worker API. Okay. Yes, sir, back here.
So speaking about chaining
Yeah. So the question was, are we considering looking at reactive streams or other mechanisms from Java to solve those problems? I'm not sure that I know exactly what the solution would look like at this point in time. I mean, I think what we've done is we've recognized that, hey, there's some additional use cases here beyond just the simple use case of I've got a task that has a bunch of pieces of work and I want to break it up and run it in parallel. But actually what tools or utilities that we would use to do that, I don't think we've really gotten that far down the path on that. So, yes.
So, I assume what you're saying, like the dash parallel would be deprecated. So this is your way of doing modern parallelization and leaving that behind. Is that right?
Yes. So the question was, would dash parallel be eventually deprecated in place of the worker API? And that's exactly what we intend to do, right? So right now, dash parallel allows you to run these non-parallelizable tasks that are in different projects in parallel. And the assumption there is that because they're in different projects, they're not going to affect each other. But there's no guarantee that that's the case. With the worker API, you get more of that guarantee. You get this sense of immutability for the work items. And so the idea of whether a task is in the same project or in another project really becomes immaterial because we know that it's pushed all of its work out there. All that work is immutable. It's not going to affect any other tasks. And so, yes, the answer is yes, that we will eventually deprecate dash parallel, assuming we reach a critical mass with things that are using the worker API. Okay. Yeah. So the question would be, if I have a task action that has a task that has a single action, and is there going to be a way that I can say that particular task is safe to run in parallel? And then what happens with tests and things like that? So, with a task that runs or a task that has a single action, I can imagine a convenience task that would allow you to do that, right? So convenience task, it basically says that, okay, whatever your task action is, whatever form that takes, we know that that's an immutable thing, and we would provide some way that you could just say, okay, I implement this task, and therefore I'm already parallelizable. Now, what form that takes, again, like I said, we're kind of early days in this. There's certain things that we haven't quite fleshed out in terms of implementation-wise, so I can't speak to that. But certainly. Now, when we talk about tests, you're already kind of in, tests are already in a state where they're safe to run in, parallel. So we could potentially, or not potentially, we eventually will probably look at taking the test task and making that parallel safe such that, he's submitting, the processing of test classes as his unit of work. Now, again, that kind of falls into that category of work of, converting Gradle tasks over to using the worker API.
You notice there's already some interface there, right? When now you set your max parallel force for tests.
Yes.
On your work account, you can bring it back down again in Gradle 4.0.
I'm not sure I understood the question. Can you?
The max parallel forks, which tells the test task how many parallel workers to use for tests.
Right.
They're being constrained by the number of workers currently, so there must be some integration there.
Yeah, so it is the same pool of workers or the same constraint that's being applied not only to tests that are being run, but also to items of work that are being run. So, that max workers that you set is a universal setting. It's controlling the level of parallelism of everything in the build. Yes, sir.
Sorry, just a follow-up to the question I asked before. What would be the isolation mode for that replacement? Would it be none or class limit?
For the parallelizable task, I would think that it would be whatever you wanted it to. I mean, it's really, the none or the class loader is really neither. If you think about what parallelizable task is right now, it's essentially none, right? Because he's using the class loader of the task. He's using that shared class loader. But you could potentially, implement the same thing but with isolated class loaders as well. So, yes, sir.
You showed an example with Java if I call project.java exec as part of my task action,
Mm-hmm.
I can start using this feature? That's correct?
No, this would be a replacement for Java exec, right? So instead of calling project.java, the question was, if we showed an example using Java exec, that if we were using Java exec, are we now using the worker API? Is that correct? Is that what the question was, or?
I want to know if it applies to, inside my task action, I call project.exec.
Right.
And I think I saw exec/Java exec, so I assume the worker API can replace either or?
No, the question.
No, so
yeah, go ahead.
the example I showed started from a task that was using Java exec that is not using the worker API. So that was the starting point. And then you don't get any parallelism by default and so on.
And then the question of whether we could use that for exec as well. The answer is no on that. It's really a replacement for Java exec. I was simply, in the slide where we were showing exec and Java exec, talking about things that, kind of create more work, which is, spawning additional processes. But, something that was doing exec, you could potentially, I'm not sure of any way that you could do that, because the worker daemon is really a Java executable, and you're providing an implementation that is a Java class to execute. Now, certainly he could then, exec other processes, but now you're kind of back in the same boat there, where
Well, what you could do is use the non-isolation mode, so you get the parallelism.
Yeah.
And inside
true.
your unit of work, you use exec. And then you get the benefit from parallelism with a little overhead, but you will have to wait for service injection,
Yeah.
basically.
So yeah, you could potentially still use exec along with it, but it's not really a replacement for Java or for the exec task or the exec convenience method. Okay, any more questions?
Cool.
Great. Thank you guys very much.
Thank you.